All right, so I've got all the homework assignments, and on Thursday you're going to submit the demand estimation, and we'll have a quiz. It'll probably be related to the homework that's submitted today. And then homework 8 won't be due until after spring break. So you've got some time to work on that. We're now in Chapter 11. And for the beginning of Chapter 11, let's revisit this idea of doing a force balance on an element of water. And we looked at a similar figure before, but when we were looking at the figure previously, the water surface was actually getting shallower in the direction of flow. Here, we've got uniform flow, which means that the velocity and the flow is not changing with respect to position. Remember how there's 3 different slopes? There's 3 different S's. Does anybody remember what are the 3 different S variables? There's S, S, and S, but they've got subscripts that go along with them. SF, all right, which is, do you remember what that stands for? That's right. Slope of energy grade line. Is the energy grade line on that figure? Which one is it? It's the one on the top, S sub F, right. It's an imaginary line that is above the water surface by the magnitude of the velocity head. Okay, so then there's SW, which is the water surface slope. Slope of water surface. This would be an excellent quiz-style question, like what are the 3 different slopes? What do they mean? And S naught, which is slope of the channel. Good. Slope of channel. Is it 1N or 2? Channel. 1, right? All right. So we've got here uniform flow, and what is this F1 and F2? Does anybody remember where those come from? Is there 2 F's? Thank you. Is it Chanel? Is that the perfume? All right. That's why I didn't become a spelling professor. One of the many reasons. All right. Thank you. So F1 and F2, where do those come from? If we are looking at an element of water and we're doing a force balance, what's force 1 and force 2?
Is force 2 like resistance to flow?
That's a good guess, but no, the resistance to flow is down here at the bottom. That's this shear stress. Yep. So anyone else want to be brave and hazard a guess about what F1 and F2 are?
F1 is the force of the water behind it pushing, and F2 is the resistance.
Same thing, but on the other side. Yeah. So if we're saying here's an element of water, and this is our control volume, what are the forces acting on this control volume of water? The water that's on the outside of the control surface is pushing on it because of the hydrostatic forces. And so there's a pressure, there's a depth, and this little triangle here, that's the sort of visual reminder that pressure is increasing in the direction of depth. And so they've put the F at 2/3 down because, you know, the centroid of a triangle. So it's the hydrostatic force pushing to the left, to the right, and then F2 is just the opposite direction. F1 and F2 here are equal because the depth is the same and the cross-sectional area is the same. And so F1 and F2 cancel out. And so what we end up with is that this shear stress is equal to the component of the weight of the water that's acting in the horizontal direction. So this flow is in equilibrium. And how quickly the water is moving depends on slope and resistance. Now, this relationship has been presented before, and I give you the little hint here that you're going to need to remember this relationship when you work on problem 1116. What it says is that we can know what the magnitude of the shear stress is if we know the slope of the energy grade line. R means hydraulic radius, and so R is the cross-sectional area divided by the wetted perimeter. And so for a trapezoidal channel, for example, the hydraulic radius would be the cross-sectional area, whatever that magnitude is, and then the wetted perimeter is just only that section that is touching the water, not including where the air is touching the trapezoid at the top. So that's what we mean by R, and of course gamma is the unit weight of the liquid. Well, oftentimes what we're not sure about is what's the depth of flow. Why not here is called normal depth. In open channel flow, there's lots of different depths, but the normal depth means what would the depth of flow be if there's nothing disturbing this flow. We don't have any obstacles at the bottom of the channel. We don't have the slope changing a bunch. We don't have the channel getting wider and narrower. It's just if we have the continuous, the same conditions in all directions, both upstream and downstream, what would the flow depth be when it comes into equilibrium? That's what normal means. Normal means assume steady, uniform conditions. And normal depth arises out of equilibrium. And so what we do is we just equate how much resistance there is to what the change in elevation is because of the channel slope. And so in normal flow conditions, all three of these slopes are equal: the channel slope, the water slope, and the energy grade line slope. And you can see that that's the case here, that these three lines are parallel. We previously knew that there was some flow resistance equation called the Chezy equation, but Manning replaced that, and we can get more accurate results by accounting for flow resistance as a function of hydraulic radius to the 2/3 power. The Chezy equation said let's take the hydraulic radius to the 1/2 power. Slope is still to the 1/2 power in Manning's equation like it was in Chezy, but here is Manning's equation both in terms of SI units and traditional units. Oftentimes you'll see Manning's equation written in terms of Q rather than in terms of velocity. And so it's pretty easy because we know that Q equals VA. And so for Manning's equation what we would say is area divided by N times the hydraulic radius to the 2/3, slope to the 1/2. So we've just multiplied this velocity expression by A, and that becomes Q instead of V. All right? If you need to, like on a homework assignment, there is a way to relate C values and N values. And so there's the equation where you just set those two, this V equals to this V, and you can relate C values and N values. But nowadays, it's pretty uncommon to find resistance defined in terms of C. And it's very common for N to be used as the indicator of roughness for open channel flow. In closed conduit flow, remember our F value always was changing depending on the velocity of the flow. It was changing depending on the diameter of the pipe. You know, F was sort of a dynamic resistance factor. N is fixed. So we don't have to calculate N. We just look it up from a table. And we don't have to account for any changing flow conditions when it comes to picking the right N value. Sometimes they'll have different N values depending on, you know, if it's a really steep channel or if it's a relatively mild slope. But in general, N values are fixed and we don't have to iterate in order to find the correct N. Here's some example of typical N values. The most common materials that engineers are faced with working with would be concrete, because a lot of circular sewer pipes are made out of concrete, and open channel flow through a sewer pipe is, you know, one of the most common things. And it's also pretty common to line channels with concrete when irrigation water is being moved around. So a really smooth concrete might be as low as 0.011. But the more typical value that you'd see most of the time when they say concrete would be 0.013. The other material that's pretty common is plastic pipe. Plastic isn't listed here, but plastic also has a pretty typical N value of 0.013 for plastic pipe. In fact, there is a special manufacturer of pipe that's used in storm drains mostly, and they design their pipe so that its flow characteristics matches concrete, since concrete is used so commonly. All right, so we have just a first exposure to Manning's equation here. Let's assume that we have a rectangular channel that is 1 meter by 3 meters. So this rectangular channel is 3 meters in width and 1 meter in depth. And we want to know how much flow can that carry if the slope is 0.01. And one thing I'll always try and confuse you with, one of my tricks on quizzes and exams is to try and confuse you on the slopes. Like I'll say slope is 1%, but in the equation it has to be a decimal form. So I've just told you my trick, right? So now I can't catch you with it unless you forget. And I always forget that sort of thing, which is why I make it one of my tricks, so that you don't have the same mistake that I sometimes make. So put that into Manning's equation. We want to know flow capacity, which means what is the flow rate, Q. All right? All right, so to begin with, we wanted to find the capacity. So we just find the cross-sectional area is 3 square meters. The wetted perimeter is that section here where the water is in contact with the concrete. That is 5 meters. So the units of hydraulic radius, if we have area divided by wetted perimeter, the units are going to be meters, and it's 0.6 meters. So the flow rate, when we plug everything in, should be 19.4 cubic meters per second. Oh, they definitely don't. Yeah, this is not a dimensionally homogeneous equation. And I'm glad that you noticed that. And so like where are the units working out? They're built into the n value. This is an empirical equation. This is not a like a fundamentally correct equation. It's just based on observation.
So just slap the dimensions we know. Because I solved it using the Cheppy equation first, and there's no seconds, it's only meters.
Yeah.
It's essentially a friction factor.
N is a friction factor, yeah. But if you're wondering how you get cubic meters per second from meters squared and meters to the 2/3 power, there's no time component here, so where are the seconds? It's just they observed a lot of different flow rates to come up with n values, and it fits the data pretty well, but it's definitely not bulletproof. But it's not. It's a dimensionally. Because it's an empirical equation. It's not homogeneous where the units are the same on both sides of the equation. All right. So on the second part of this example, I asked the question: what channel width is required to convey a flow rate of 30 cubic meters per second? So that changes things around a little bit. Instead of solving for the flow rate, we say we've got Q equals A over N, hydraulic radius, which is area divided by the wetted perimeter, to the 2/3 power, and slope to the 1/2. So now we know that we want the flow to be 30. So how wide should the channel be? We're going to keep it at a 1 meter depth. So Y still is 1 meter, but the channel width B is what we don't know. So how wide should it be? We're still going to have the same slope as 0.01. So for 30 cubic meter per second conveyance, we have 30 cubic meters per second is equal to B times 1 divided by our N of 0.011. And then the area is B times 1 divided by 2 plus B. And that's to the 2/3 power. And the slope is still 0.01 to the 1/2 power. So the B value here is going to be 4.264 meters. In a minute, I'll show you how to solve Manning's equation on the Casio calculators. Well, I won't. Dr. Pearson will. He's the special Casio expert that is going to deliver a recorded guest lecture. But you can put in equations like this and solve for one of the variables. And so that is going to be the width. Now, what you'll notice, though, is that if we had just scaled the flow per unit width from here, if we said we got 3 meters was the width and we got 19.4, how wide should it be if we want to get 30? If you thought of it this way, you'd get the wrong answer. You would have gotten that the width required is 4.64. But what that would fail to account for is that when you make this wider, like we've just done over here, what we found is that it needs to be 4.264. When you make it wider, the flow area in the center is now further away from these edges where there's a lot of resistance. And so you can't just make it twice as wide and assume you're going to have twice the flow capacity. If you make it twice as wide, actually you're going to more than double the flow capacity because you're going to be getting the flow further away from the edge resistance. So there are sort of edge effects that come into play. So don't do this method. In fact, I hesitate even showing you that because it's not the right way. You always have to put it into Manning's equation because Manning's equation accounts for the edge effects of having a rectangular channel where there's resistance not just at the bottom but also on the sides. Okay. Any questions on this first example? So here's some more N values. These are the ones from your textbook for channels. When there's flooding, like there has been recently, did anybody check out Route 60 when it was closed over the weekend in Barbersville? A big highway was completely submerged. It was pretty interesting. I should have taken pictures, but I didn't. But I did see it. Overbanks, like you can have grass, crops, brush and trees, dense brush. There's a wide range of resistance values depending on the size of the obstacles and the amount of resistance they impart to flow. Another way, besides looking up the information from a table, is if you know what the channel is being lined with, like if it's gravel or some sort of an aggregate, there is an estimated relationship between the grain diameter of the aggregate and the N value that corresponds to that. And so here is the empirical equation that estimates grain diameter to the N value. And just to illustrate what that's like, if you had a particle size of 0.5 inches, you'd need to convert that to feet, and then you can put the feet into d sub m and solve for the N value that corresponds to that. So let's say that you've got a median particle size of 0.5 inches. So that would be sort of like the diameter of pea gravel, maybe a little bit larger than pea gravel. So the way that you use this equation is you say d sub m is 0.5 inches, which is the same as 0.5 divided by 12 feet, which is 0.04167 feet. And so N is going to be 0.34 times this diameter of the grains in feet to the 1/6 power. So that is an N value of 0.020. And if I remember correctly, there may be a homework assignment where one of the problems where you have to find the N value as a function of the grains that are specified. So there's that. But here is really the meat of today's lecture is finding the unknown depth for a trapezoidal channel. It's easy for a rectangular channel. Rectangular channel, the geometry is simple because there's a linear relationship between depth and cross-sectional area. In a trapezoidal channel like this, there isn't a linear relationship. For each meter that it gets deeper, the top of the channel is also getting wider. And so you're accumulating ever more cross-sectional area with each additional meter of depth. And so to illustrate that, let's take a look at this example where we've got 175 cubic meters per second going through a trapezoidal channel. And I bolded 175 because I think in the notes it said 17.5. If it does, change that to 175. Before we dive into this example, are there any questions over any of the previous slides?
If your values are presented in meters, do you need to convert that to feet in order for the equation?
So N values are, it doesn't matter whether it's SI or BG. The N values are good. But what you'll notice is that there is this 1.49 that you use if you're working in BG units. So BG units, length are feet, slope is unitless, and you can use the same N values either way. You don't have to convert the N values. But then the velocity you'd get would be feet per second instead of meters per second. Yeah?
When you use the Manning equation for M, does the D value have to be in feet then?
For
Just for example.
this one. This one has to be feet. The diameter has to be feet. So this .034 is calibrated assuming that the diameter would be feet. We could find a different coefficient there in meters, but that does require feet here in order to get the N value, which is itself interchangeable. Was there one more question? All right, so we have a trapezoidal channel, and the tricky part is that when it gets deeper, the top gets wider. So we've got a trapezoidal channel. It's carrying 175. The slope is 0.45%. And we want to know how deep is the water going through there. And I want to lead you through, okay, if we rearrange the Q, so what's R? What is the formula for R? It's something divided by something. Area divided by wetted perimeter, right. So this is area to the 3/3 power. And inside of R, if we have R to the 2/3 power, that's the same as if we have area to the 2/3 power divided by perimeter to the 2/3 power. So R to the 2/3 is equal to area to the 2/3, P to the 2/3. So over here, this area to the 5/3, that's not like some magical thing. That's just because we're combining the 3/3 here and the 2/3 that are in the hydraulic radius together. And that seems like a weird thing to do, but trust me, it actually makes our job simpler when we are solving for an unknown depth. Because the depth, y, goes into both area and perimeter. So y is going to be one of the variables that goes into both of those terms, and it's better to keep it separate when we are solving for depth. So I wanted to point out that these are equal, and it's a pretty easy translation to go from this first equation to the second one. And then where does this come from? Just by moving all of the factors to the left-hand side that are dependent on y, because the area depends on how deep it is, y, which is unknown. The perimeter, the wetted perimeter, depends on y, which is unknown. And then all of the known values are on the right side of the equation. N is given in the problem statement. Q, given. Slope, given. So we're going to have a fixed quantity on the right-hand side, and we're just going to keep playing around with y values until we get both sides of the equation equal. That's going to be our strategy in Excel. And so specifically, let me write a couple of things on the board here. From the t value that you see there, that's defining the side slope. It's saying that it is a 1 to 2 side slope. So t equals 2. That means w, which is 1 plus t squared to the 1/2 power, is going to be the square root of 5, which is 2.2361. Now, area to the 5/3 power. What's the area of a trapezoid? If we go to the formula that's on that sheet I gave you previously in the notes for each of the different shapes, it says the area to the 5/3 wetted perimeter to the 2/3 is equal to Q N and slope to the 1/2. Okay, so the area to the 5/3, that is B plus Ty times Y. That's area. Take it to the 5/3 power. Wetted perimeter, B plus 2YW to the 2/3 power. Again, if you don't remember where those formulas are coming from, it's coming from this table. So look, trapezoid, it's saying area is B plus Ty times Y. So here's A. Perimeter, it's saying B plus 2YW. There that is. So we're going to have that equal to 175, which was our flow rate, the n value of 0.013, and then the slope of 0.0045 to the 1/2 power. So B is known in our example. T is given, W is given. The only unknown here is going to be Y. So let me illustrate how we can use Excel to find the depth Let me take this. Okay, so we need to have the B value, which is in meters. We're going to have N, the slope, our flow rate, which is cubic meters per second. We're going to have a W value. And so from what we have written on the board, or the problem statement, we know that the channel width is 15. The N value is 0.013. The slope of the channel is 0.0045. Our flow rate's 175. And the W is 2.2361. We could have calculated that here in Excel, but since I already have it on the board, I'll use it. So I'm going to have the left-hand side of the equation, the right-hand side of the equation, and then the difference. The right-hand side's easy, so let me start with that. Equals N times Q divided by the slope to the 0.5 power. Okay, so there I've got the right-hand side. Any questions so far? Oh, not really. Yeah, I just think it looks awesome that way. All right. So now I'm going to type this equation with the B, T, Y, all of that. I'm going to type for the left-hand side. When I say left-hand side, I mean this one right here. All right. So equals, not equals, parentheses, parentheses. And the trick is always putting the parentheses in the right spot with Excel. Its order of operations is the tricky thing here. So B times T. Oh, I don't have T in there, do I? All right. T equals 2. All right. Okay, so B plus, oh, and I also need to have a guess for Y. The formula will always tell you what you need to have. Okay, so Y. I don't know what the depth is, and so I'm going to start with a guess of maybe it's 1 meter. Who knows? Okay, so here we go. Finally, I think I'm ready to type it in. B plus ty, t times y. Okay, now I'm going to close the parentheses there and times all of that by y. And then close this parentheses, and it's to the power of 5/3. Okay, so I've written here the numerator of the left-hand side. And then divided by b plus 2 times y times w. And this one is to the 2/3 power. All right. Now, fingers crossed that I typed it in right. Any questions before I press enter? All right. So they're not equal. That doesn't necessarily mean I didn't type it right, because remember, y is just a guess. How different are these two? We've got to iterate until we get the correct left-hand side and right-hand side equal. So is it less? If I do 0.9 instead of 1, does my difference get bigger or smaller? So we'll put 0.9. Okay, the difference got worse, which means actually 1 is better than 0.9, but 1.1 would be even better. 1.2, even better than that. What's the smart way for me to solve the rest of this problem? Right, so if I go to either solver or goal seek, I'll do data, what if analysis, goal seek, and my goal is I want this difference to be equal to 0. And I'm going to let the spreadsheet optimize the depth, just keep playing around and check lots of different guesses of y in order to do that. Okay, so it's finished, and 1.573, that is the correct depth. So that is what the flow rate is going to be in our trapezoidal channel when we've got a certain slope, when we've got a certain n value, a certain width. If we changed any one of these parameters, then the depth is going to be different. So for example, let's say it's a flooding day like today. Instead of 175, maybe there's 300 cubic meters per second. What do you expect if we change this to 300? Should the depth be higher or lower? When there's more water going through the river, is the river deeper or shallower? Yeah, I see a thumbs up. It's getting deeper. So let's try that. We'll do the what if analysis again. Goal seek, we want the same thing. We want our difference to be 0 by changing the depth. So we're expecting that it should be, instead of 1.57, something higher. There it is, 2.14. Okay, so it makes logical sense to us that if you have the flow rate higher, there would be a greater depth. What if we made the slope steeper? Anyone want to guess what happens if you make it steeper slope? What will happen to the water depth? It will go down. Why? That's true, but why does the water depth decrease if you make it steeper? The velocities increase. You make it steeper, the water's going faster. You know, it's like rapids, you know. So if you make it steeper, the water goes faster. So for the same flow rate, a lower depth is required because continuity relationship says Q equals V times A. So the depth will go down since the velocity went up. So let's try that. What if we make it steeper? This right now is 0.45%. What if we made it 4.5%? So 10 times steeper, 0.045. Okay, so I'm going to solve for depth again now that I made it steeper. Goal seek. We want the difference to be 0. I wish it would remember that by changing this. Solve. Okay, so if we make it a slope of 4.5%, then the depth would only be 1.1. So you get the idea. If you change something, then it causes the flow depth to change. Excel. It's a great tool. All right. Any questions about this example before we move on? Oh, by the way, I still owe you 2 minutes from last time. Although it could be argued that getting the whole day off is maybe weighing out the 2 minutes that I took from you the previous lecture. But I'll give you those 2 minutes and the day off. That's how generous I am. Yeah.
How does it act if you treat it as if the water's free falling?
Free falling. The slope. No flow?
Be 90 degree slope, right?
Like if it's free falling, I think it gets undefined. I wouldn't even know what to put on the slope. Would it be infinity or would it be 0? 1? No, 1. 1. Yeah. All right, so just to summarize, what we're doing in finding the normal depth is we are solving for some unknown y. And if you're using BG units, the only difference is you've got 1.49 is the prefix that's needed to get all of the units to work out. Here's the table 10.1 that you should have highlighted in your textbook because we're going to come back to this several times through the semester. Okay, this is the one where I said I've got a video from Dr. Pearson. He knows how to use those Casio calculators. I don't. I never will. My calculator is so different from yours that you wouldn't know how to use my calculator and I don't know how to use those. I use an HP calculator, and it actually, you type in the values in something that's called RPN. Has anybody here ever heard of RPN before? It sounds like a joke, but it stands for reverse Polish notation. And if you want to do 1 plus 1, you type in 1 plus 1 equals, right? Not me. If I want to do 1 plus 1, I type in 1, enter 1 plus. And it just, there's fewer keystrokes if you do the RPN, but the disadvantage is if you do it enough, then you can't even think in algebraic mode anymore. So it's really hard for me to use a calculator like this. And so I let Dr. Pearson explain to you how to solve the Manning's equation for this example. So let's do another example, and instead of solving it with Excel, let's solve it using the calculator, trying to solve for the unknown depth. So this is the same basic idea as before. We've got some channel width. This is 3.5 meters wide. The slope is 0.1%, which means 0.001 is the S value that we're going to enter in. We've got smooth asphalt, which corresponds to an N of 0.014, and then the side slopes of 2.5 to 1. That means that the T value is 2.5. Okay, so let's watch this example. So follow along with your calculator. I think this is the same example that he solves. Fingers crossed.
This little video, I want to show you how to use the Casio FX115 to solve Manning's equation for a trapezoidal channel. The equation is given to me by Dr. Wade is shown on the screen. In order to use the Casio, we have to do some translations of the variables. We don't have a Q variable, for example, nor do we have a T. We do have a B, C, D, X, and Y, so we'll do some translations here. The equation will be A equals, notice we got to use the alpha button, and a couple parentheses to make sure operations get done in the correct order. B, which is going to be used to represent B in the...
Do I need to bring the lights up? I want you to be able to follow along. Is it too dark in here? You can see? All right. Anybody need to write this equation down? Because it looks different when you have it in terms of A, C, all that weird stuff. Okay.
Original equation. A is being used to represent Q.
By the way, if you haven't noticed already, up here at the top is a summary of the keystrokes that he's used so far. Not that, but there.
Plus T times Y, but in this case T is really variable C on the Casio, and Y is Y. Close the parentheses and multiply that again by Y. Close the parentheses and raise all that to the 5/3 power. Since I'm in the math I/O mode, I can make it look pretty much like the equation in its original form. So I'll put the 5/3 power, hit the cursor control to the right a couple times to get back down on the the main line, and then multiply that by the square root of S, which in this case, I'm letting D represent S. Hit the right cursor control to get out from underneath the radical. And then divide by the denominator, and I need a couple parentheses to make sure the operations get done in the correct order. Oops, I only need one to begin with. X, which is being used here to represent variable n. Multiply that by left parentheses B plus 2 times Y times the square root. Again, I'm in the math idle mode, so I can make it look pretty much like the original equation. 1 plus C, which is being used to represent T, squared. Get out from underneath the radical. Close the parentheses. Raise that to the 2/3 power. Get out from underneath the, away from the exponent. Close the parentheses. And say comma Y, which is shift right parent alpha Y. And hit solve, which is shift calc. I've already solved this once. So I already had A equal 29. If I hit enter that value again, B equals 3.5.
So these are the values from our example, right? We've got a flow rate of, let's just double check here. 29, yeah, 3.5 width. The side slope should be 2.5, and the slope is 0.001. So let's go back here.
Enter a new value. C equal 2.5. Enter a new value. D is equal to 0.001. X equals 0.014. I'm going to put a starting value in like 0 for Y, since I really don't know what the answer is. And when it solves it, it comes up very quickly on the emulator as 1.6577, probably 10 to 20 seconds on your calculator. If I hit shift solve again, and enter the same values for everything except Y, maybe I'll enter a stupid value like -3 and hit solve. It's going to come up with a negative answer. That simply means that there's another solution, impractical or nonsensical solution that you need to ignore. So give it a good starting value. Shift calc, put in value for A, B, C, D, X, and for Y we'll put in 1 as a starting value. And notice we come up with the right answer.
All right, not too shabby, Dr. Pearson. You'll have to tell him thanks next time you see him. The link to that is right here. If you need to watch it again, you can.
The class.
I guess you don't need another lecture.
6th of October, Friday.
All right. Usually what I would do, the document camera isn't working this semester, but I bring out like my awesome calculator and show you how much better it is than the Casio, but I won't do that this semester because we're running low on time and because the document camera is broken. So the flow rate for this one, or the depth, 1.66 meters. Was anybody able to follow along and get the same thing? How long did it take to converge? 30 seconds? Bless its little heart. Watch batteries are almost all drained now. You gave it such a hard calculation to do. Yeah, you need to put it out in the sun. Well, you got a cloudy day. You're in trouble. All right. Well, I'm glad it works. All right. This channel's not looking so good. What we've got is a lot of scour here. And a lot of the streams in the local area probably look similar after today. When you've got a big storm and the flow rates are big, the water depth increases, and so more of the flow is far away from these resistance areas. And so there can be a really high velocity when the flow rate gets higher, the velocity increases, and that puts more shear stress on what's left behind. So shear stress, as we saw earlier in today's lecture, is the relationship between unit weight of the liquid, the hydraulic radius, which is channel geometry, and then the channel slope, S naught. Oftentimes, you'll see problems that are asking how steep can the channel be for a certain material, or what's the maximum flow velocity for a certain material. And the reason for that is it's possible to do a geotechnical analysis and estimate the cohesive strength of soil, how well it's going to stick together, and then relate that to what's happening with the water. In other words, as the water is flowing down the channel, the water is pushing on the material, and the material has to be able to resist that shear stress, or else there will be scour. So Manning's equation can be rearranged to solve for maximum allowable velocity to avoid scour. And if you do that, as we will with this example, then you're able to calculate how much velocity is going to be right at the verge of imminent scour. So in this example, we've got a maximum permissible unit tractive force. What that means is that if you go above 10 newtons per square meter, then the soil starts to be scoured downstream. It's going to start to erode. And we know that the maximum velocity is going to, as the velocity increases, so does the shear force that's applied to the soil. And so what I'd like you to do is use this shear stress relationship and Manning's equation in order to solve for what is the maximum velocity. So in the shear stress, what we know is the slope of the channel geometry, maximum over a channel of this material. We don't know the width here. Let's see. Oh yeah, okay. The hydraulic radius actually can be calculated without knowing whether it's trapezoidal, without knowing whether it is rectangular, because it's just going to be the slope and the unit weight that you can use to calculate the shear stress. And so with the first equation, you calculate R with the given 10 newtons per meter squared, and then substitute that R into Manning's equation to solve for the velocity. Okay, so we find that the hydraulic radius for the shear stress and the unit weight and the slope that's described, the hydraulic radius is 0.068 meters. And then substitute that into Manning's equation for velocity and get maximum velocity of 1.02 meters per second. So what happens if the velocity is bigger than that? It'll begin to scour, which means sediment transport. It means that the particles that can be lifted up by the water, it'll start with the smaller particles. It'll start to move those small particles, and then it'll take the larger ones after that. Okay, any questions before we wrap up for today? Okay, there's lots going on. Remember that on Thursday, you're going to need to submit your demand estimation. And then next week is spring break. So I will see you on Thursday.